So, in the last class I made an announcement that okay, the second order test for deciding whether a point, critical point, that is the one which satisfies gradient of f is equal to 0, such a point x naught y naught, whether it is a maximum or minimum or local maximum, local minimum or neither of them, a saddle point, how do I decide? So, I said okay, we do not have time, so we will push it in the next class and all these sort of things. But I realized that as you grow old, you possibly forget your own well planned stuff. Then I went back and looked at the lecture series that I had planned, and I found that actually second order conditions had been there is a separate lecture for second order conditions. So, as we start the 4th week, we are actually, our lectures would remain as planned, there will be no change, which is a good stuff of course. So, here we are going to discuss second order derivative test for maxima and minima. Second order or second derivative test, I am not writing second order, I am just writing second derivative test Now, here as always we will consider a function f from R2 to R. This taking of just two variables is a very important marker in the sense that it gives you an idea of what things are happening. But going to a higher dimension, whatever you can do in this particular case in optimization in 2 dimensions, such things may not be carried so easily to the 3rd dimension, may not be done for higher dimensions. So, 2 dimension has a speciality where you can handle things much more simpler with much more and look at things much more simply than what you can do in higher dimensions. So, we will start by considering a point x naught y naught which is a critical point. So, what is a critical point? You know what a critical point means, something which satisfies. So, this would imply that the gradient, critical point is something which satisfies that the gradient of f at x naught y naught must vanish. That is, the gradient of f at x naught y naught must vanish, which put in much more simpler form means the first derivative of f with respect to x, the first partial derivative evaluated at x naught y naught is 0, and the second partial and the first partial derivative evaluated with respect to y at x naught y naught is equal to 0. We have shown that any point satisfying this, unless you have assumption of concavity or convexity, you need not have them to be a minimizer. So, now assuming that x naught y naught is a critical point, that you know that x naught y naught is a critical point, how do I think of moving ahead, right? So, the way to move forward is the following. So, first, knowing that del f del x at x naught y naught is 0 and del f del y at x naught y naught is 0, let us write down the second order Taylor's theorem. So, Taylor's theorem will have a key issue here, second order Taylor's theorem. So, here that any term with del f del x and del f del y at x naught y naught will not appear. So, we are looking at the point x naught y naught and we are looking at the expansion of f of x y. Which is now Now, the second order term we can write it like this, we will write down what is A and B and all these things as we go on, because these terms will become important. Of course, a lot can be done in terms of inner product, but okay, we will not get into such details at this moment. Plus R2. So, where A is half of the second derivative of f at evaluated at x, my del 2f del x2 evaluated at the point x naught y naught. So, we just for brevity of the writing we wrote that. B is half of del 2f, the mixed partial derivatives, and we are assuming that everything is continuous and nice, because unless we assume like this, Taylor's expansion is not really possible. And so, this evaluated at x naught y naught, the second derivative of y, del 2f del y2. So, these are we mark, these are what is there, and R2 is the error term, R2 is error term, so that it vanishes as x naught y naught approaches, xy approaches x naught y naught, this term vanishes much faster than xy approaches x naught y naught, which means if I write h as a vector x minus x naught and y as a vector y minus y naught, R2 is actually small o of norm h whole square, which means R2 by norm of h square goes to 0 as norm of h goes to 0 or h goes to 0, whichever way, whatever you want to write. So, the error term, what it says that R2 must vanish faster than h vanishing, that is, and in the second order term means R2 must, the way the quadratic is the norm square of h cannot vanish faster than R2, R2 must vanish faster than the square of the norm, which is a very, very important thing to observe. So, now instead of taking any arbitrary critical point x naught y naught, for simplicity we will set x naught y naught to be 0. X naught y to be the origin 0 0. Now, if I put 0 0, now I will put 0 0 here, x naught y naught equal to 0 0. So, let us see what the expression will become. So, this expression will become f of x y. So, x y suppose is a point very near 0 0. So, it will become f of x naught y naught, which is now 0 0. So, I will write this as f 0 0. So, it will become f 0 0 plus a x square, x naught is 0 and y naught is 0. So, it will become a x square plus 2b x y plus cy square plus R2. When xy is very near 0 0, in a very small neighborhood around 0. So, if I take the point 0 0, this is origin, right, 0 0, and I take a very small disk around all points inside this circular disk except the one in the boundary. Now, as you make this radius shorter and shorter, you go nearer and nearer into 0. The more near you go to 0, the R2 value diminishes very fast, it goes to 0 very fast. So, for xy very near zero zero, R2 for all practical purposes is almost 0. So, this is a very crude way of writing. So, we are also making a crude description, very crude way of writing. And then what I would have that fxy can have an approximation they are almost same. So, when xy is very near 0 0, the functional value is very well evaluated by its quadratic approximation. So, this point, this part is called the quadratic approximation of f around 0 0. So, now what is happening that if suppose look at the function ax square plus 2b xy plus cy square. Now, for a given choice of xy, for example, if we can do that, if we can prove that this is 0 0, if for some xy very near 0 0, if I can prove this, this simply implies that fxy is in some sense greater than f0 0. So, f0 0 becomes the minimizer. So, this is a very crude sense, you cannot say this implies this, but in a very crude sense this is the meaning. So, essentially I have to determine a kind of sign on this, I have to see whether what happens. So, basically it tells me that the graph of f, the function f near 0 0 looks almost like the graph of ax square plus 2bxy plus cy square translated by the amount f 0 0. So, here is a quadratic function, basically this looks like some kind of a quadratic function, this say a function of 2 variables. So, graph would be something like this, function of 2 variables, and basically now this is your x naught y naught. So, around x naught y naught the function values almost match the function value. So, around x naught y naught here if you magnify this zone, if you magnify, you will see the function values differ by a very less margin. So, when x naught y naught xy is very near x naught y naught, means suppose in this zone, then what can happen is the following. Then in that particular zone, the graph of this function ax square plus 2bxy plus cy square almost coincides with the function value, and at 0 0 it coincides with f0 0, because fxy, if you write it like this, if you consider this is nothing but just take this part, then when you put x equal to 0 and y equal to 0, it is f0 0 at x equal to 0, y equal to 0. At x 0 0 this thing matches with the function value. At other places there is a very small gap, it is so minute that you really for all practical purposes you do not bother. So, sorry, I am making a mistake, maybe this should be my point 0 0 actually, this is 0 0, so this should be the origin, not this one, I am making a mistake. So, I am writing as if it is for an orbit point x naught y naught. So, this is the x axis, y axis, z axis. So, this is a kind of quadratic function. So, around this point 0 0, very points this, at 0 0 the function value of fxy is f0 0 of this function, of the quadratic function value, the quadratic function matches with f0 0 at 0 0. Apart from that, the quadratic function does a very good, or whichever way, this way or that way, it could be like this also, the matching could be like this. That is depends on whether this is greater than 0 or lesser than 0, it is kind of maximization, minimization sort of thing. So, this is a very crude writing, don't take it seriously. This is a kind of intuition you try to build up. So, you want to say that okay, very near 0 0, the graph of the function f looks almost like the graph of ax square plus 2bxy plus c. So, what we should now do, investigate when can 0 0 become a maximizer or minimizer, or saddle point. I am talking about local, of course, in this local sense. Global is also local, but local is not global. So, local or saddle point. Saddle point of this function gxy is equal to ax square plus 2bxy plus cy square. Please understand that we have now transferred the problem from that of the function f to that of the function g, which is the quadratic approximation, and we want to know whether 0 0 is a, when is a 0 0 minimizer or maximizer. Saddle point, when you say 0 0 is a saddle point, that if in the neighborhood of xy, this is not the saddle point that we really speak about in modern optimization theory, but in calculus that is what is viewed as a saddle point. So, if you take a point 0 0 say and take a small neighborhood around that point on the disk, right, you take a neighborhood. So, if for one point the function value becomes positive and another point the function value becomes negative, then we say that the function value, and the function value is suppose 0 0 at f 0 0, and then one value it becomes negative and for another value it becomes positive, then we say that 0 0 is neither a point of maximum or minima, it is a kind of saddle point. Okay. So, this is what is the current definition of a saddle point used in calculus when you are talking about maxima and minima more than one variable, right. Now, let us investigate this function. So, let us investigate gxy. So, observe, first thing that you observe is g of 0 0 is 0 0 is 0. Let us now observe what is the value of del f del x. Del f del x is 2ax plus 2by, and del f del y is equal to 2bx plus 2cy. Now, it is clear that at 0 0 del f del x at 0 0 is 0 and del f del y at 0 0 is 0. So, which means that 0 0 is a critical point, which means that 0 0 is a critical point. Okay? So, once you know this fact, we have to do some more work. I have not told you that 0 0 is the only critical point. So, but it is good that if I have 0 0 to be the only critical point, that makes much more easier. So, what is the condition under which 0 0 cannot, 0 0 is the only critical point. Now, let x dash y dash be another critical point. that is the partial derivatives vanish at x dash y dash, del f del x at x dash y dash is must be 0. So, 2 a x dash plus 2 b y dash is 0 and del f del y at x dash y dash must be 0. So, 2 b x dash plus 2 c y dash is equal to 0. So, you have these two equations, so equations 1 and 2. So, multiply the top equation by c and multiply 1 by c and 2 by b and subtract them to get an equation of the form ac minus b square into x dash is 0. So, you multiply the first equation with c and the second equation with b and then subtract that from 1 from the 2. So, you will get this condition. Now, if ac minus b square is not equal to 0, it implies x dash equal to 0 and from a similar argument just do the opposite thing, right. So, multiply the top equation by b and next equation by a, right, and then subtract them to get the similar sort of thing. So, from a similar analysis, from a similar discussion basically, a similar demonstration, we will also have y dash equal to 0. So, if AC minus B square is not equal to 0, then whatever be the critical point, it does not matter, x dash is equal to 0 and y dash is equal to 0. That is the key idea. So, what happens if I do not have this condition? So, my condition would be, so what happens if AC minus B square is equal to 0? Then there can be a situation where there are more than one critical points, and that is exactly what I am going to demonstrate here through an example on the board. So, consider, so I write fxy is equal to y square plus 1, write fxy equal to y square plus 1. So, you can evaluate the partial derivative, del of del x is 0 and del f del y is 2y. Okay. So, which means y is equal to 0, any y equal to 0 will make del f del y equal to. So, whenever y is equal to 0, whatever x you take, it does not matter, this del f del x is anyway always 0. So, it does not matter whatever be your x, it does not matter. So, y equal to 0 is, so any x and y equal to 0 is a critical point. So, the x axis, all points on the x axis is the critical point, all points on x axis, all points on the x axis is the critical point. X axis, all points on the x axis, all points on the x axis are the critical points. So, what about this AC minus B square? So, we will check up that part also, what is this AC minus B square. So, let us do what is del 2f del x2, del 2f del x2 is 0. So, A is equal to 0 because A is half of this. What is del 2f del y del x, sorry del 2f del x del y is 0. So, b is 0 because half of this is b. And what is del 2f? Del 2 f del y2, it is 2. So, c is half of this, so c is 1. So, AC minus b square is 0 into 1 minus 0, which is 0. So, here is a situation where AC minus b square is 0 and hence we have more than one critical point. We can have more than one critical point. But we will be happy just to keep one critical point, that is 0 0. We will be working with that and then testing whether it is maximum, minimum, whatever, local minimum, local maximum. Here it will be global maxima, in fact global minima, global maxima. So, here we will always work with the premise, we will always assume that AC minus B square, this is a holy grail, this is what we have to assume as we go along. This is, so 0 0 is a unique critical point. This is something, so our assumption now would be AC minus B square is equal to 0. See, we will only really look at this issue of when is 0 0, which is actually a critical point of ax square plus 2bxy plus cy square is actually a maximum, minimum or saddle point. And once we know that, we can talk about the other things, our own function that we have just seen. So okay. Now, when you have this condition that AC minus B square is not equal to 0, it implies two situations, either AC minus B square is greater than 0 or you have AC minus B square less than 0. There are two situations now, either AC minus B square is strictly bigger than 0 or AC minus B square is strictly less than 0. We will deal with these two situations separately. Okay. So, first we will go to the case where AC minus B square is greater than 0. So, it is basically kind of this Musuddin-Lal's this Office, the television serial which came long ago in Doordarshan. So, basically when AC minus B square is strictly greater than 0, तब फिर भी दो बातें होगी. One is A greater than 0 and one is B greater than 0, A less than 0. You have to observe that if this is greater than 0, it would imply that A is not equal to 0 and C is not equal to 0, because if A or C, any one of them is 0, then it tells me that minus B square is strictly greater than 0, which cannot be, because B square is non-negative. So, minus B square cannot be strictly greater than 0, it has to be negative, less than or equal to 0. So, there will be a contradiction. So, once I have this condition AC minus B square is strictly bigger than 0, A is not equal to 0 and B is not equal to 0 follows immediately, that these two quantities cannot be 0. Okay. Now, once I know this they are not 0, I will make a small manipulation of gxy, knowing that A is not equal to 0 and C is not equal to 0. I will write this as, I will break this up as, I will write this as x square plus 2b axy plus c by a whole square. Now, you can do all these square completions and all this, subtract something, add something to this, subtract something to that, and which I am not going to do because I think you should be able to do this yourself. I am sure all of you know this much of math. Those who are observing this course, my brother should have a little bit of inkling of what is going on. So, this is what I have at the end after doing the little manipulation. So, add for example, b by a x square here, sorry, b by a y square here, and subtract b by a y square again, and then you have this. So, here is the stuff. Okay. Now, a is not equal to 0, so but there can be two cases. One, a is strictly bigger than 0, and one, a is strictly negative. So, अगर ac minus b square strictly bigger than 0 है तब दो बातें होगी. One is a greater than 0, strictly greater than 0, or a strictly less than 0. So, if a is strictly less than 0, again in a much lighter form दो बातें नहीं मतलब दो बातें हो जाएगा. So, what is that? That when a is strictly bigger than 0, and c is also strictly bigger than 0, because if c is negative, then ac becomes negative, then the whole thing becomes negative. So, it shows that ac minus b square is less than 0. So, that cannot happen. And when I have c strictly bigger than, sorry, when I have c strictly bigger than 0, and what do you have? So, ac minus b square is strictly positive, a is strictly positive, a is strictly positive, you have gxy, right, is this whole thing is greater than equal to 0 0. If this whole thing is gxy is greater than equal to 0, which implies gxy is greater than equal to g 0 0. So, 0 0 is the minimizer. So, 0 0 is the minimizer. Now, if a is strictly less than 0, it also फिर भी दो बातें ही होगी. If so, c is strictly less than 0, because then if c is strictly bigger than 0, this will become negative and this will become negative, the ac minus b square. So, c is strictly less than 0, and so if this is positive and a is negative, then this whole thing is negative. Then a is negative, then this whole thing is negative, because this part is x plus b by a y whole square is positive. So, which means it will give me that gxy will become less than 0, because this whole thing is negative, which implies that is for all xy, do not worry, it is just for all xy. If this happens, then for all xy I have gxy less than 0, and so gxy is less than g 0 0, or 0 0 is the maximizer. So, in short, if ac minus b square is positive strictly, and as I know, then as a cannot be 0, then if a is bigger than 0, then 0 0 is the minimizer. If a is strictly less than 0, then 0 0 is the maximizer. This is what we have to keep in mind. Okay. Now, what happens if a is ac minus b square? Now, what happens if ac minus b square is strictly less than 0? I will again reiterate the fact that ac minus b square is chosen not to be equal to 0 to maintain the fact that 0 0 is the only critical point. This has got something related to strong convexity or strict convexity. All this convexity actually comes in. Convexity is certain thing in which you cannot avoid while you are maximizing or minimizing function, convexity and concavity. It comes in very subtly. Here it actually comes in a very local sense, but here we are essentially determining the for quadratic function, determining the concavity or convexity of the function. So, convexity would give the minimum, concavity will give the maximum. This is a real thing, that is a deeper thing, but here we are not going to get into those deeper issues, but tell you this very simple thing what we can do on a very simplistic approach. Now AC minus B square strictly bigger than 0 is resolved. So, I have to look at what is AC minus B square strictly less than 0, that has to be resolved. See the examples for this kind of this particular case and the proof of the Taylor's theorem, that would be put up on the, I will write down and that will be put up in the what is that called, in the portal, right. So, let us look at that. So, I know that A is not equal to 0. So, anyway this expression is always valid, that we have already written in green ink. Now, let us look at write in blue ink in this particular case. So, if A is not equal to 0, this expression is valid. This is a valid expression. We just need A not equal to 0 for this expression to be meaningful, and when AC minus B square is strictly less than 0, A cannot be 0, right. If A is not equal to 0, then this is a valid expression, right. So, if AC minus B square is strictly less than 0, there are 3 situations. A is strictly bigger than 0, A is strictly less than 0, and A is equal to 0. So, when these two cases are taken, then this is a valid expression, this expression is valid. This expression Gxy is equal to this expression is valid because A is either positive or negative. So, we will start dealing with the case if A is negative and of course, or A is positive, and start dealing with the case A is negative. So, I have just written on for A is negative. If A is negative, let us see what happens. A is negative, two things are there. A is negative, then this part is negative, and because AC minus B square is negative and A is negative, that will make it positive and this part becomes positive. A is negative, then the two things will happen. One is that A into x plus B by A y whole square is negative, and at simultaneously AC minus B square by A y square is non-negative. So, again do batein hogi if A is strictly less than 0. So, now let us consider x and y, the points x y very near the point 0 0 in that circular disc around 0 0. So, take x not equal to 0 and put y equal to 0, then g of, because this is valid because A is strictly less than 0, g of x0 is equal to ax square, because A is strictly less than 0, this is also strictly less than 0. Now, choose if x is equal to minus b by, see the idea is that when you put y equal to 0, you take away this term and take this term out. And now, if I choose, I want to now just keep this term and take this term out. Basically, what I am trying to show that there are some points around x very near to x, very near to 0 0 where the function value is negative. There are also certain points around 0 0 where the function value is positive. So, when this condition occurs, AC minus B square is strictly less than 0, what I have is a saddle point. So, let me put x is equal to minus b a by y. So, this part of gxy will vanish, that will imply that gxy is equal to AC minus B square by A y square which is positive for all y not equal to 0 or greater than equal to 0, whichever, if y not equal to 0. If y is 0, then this is strictly greater than equal to 0. Okay. So, because we are taking points around 0 0, so we are not taking y to be 0 either, because 0 is y is 0 only at 0 0 point. In a small neighborhood, we will if we take a point very near y when x 0 0, but keeping y positive or y negative but not 0, then this is what we will get. If y is not equal to 0, this is what I will get. So, I show that, so here for any x 0 I will have this negative, and basically what I have showed here is that this one g of minus b a by y is strictly bigger than 0 if y is not equal to 0, when y is very near 0 basically. So, for all y very near 0, when y value is very near 0, this is exactly what you will have. So, so in the neighborhood of 0 0, the function can take a positive value and negative value when AC minus B square is strictly less than 0, which makes x naught y naught a saddle point. So, what for the case a strictly less than 0? So, here for when a is strictly less than 0, it implies that x naught y naught is a saddle point. Now, for a positive, you do the stuff, absolutely, try it out, try out the argument, you do the stuff. It is fun, do not worry. Now, let us look at the case a equal to 0. Now, when you have, see, a can be 0 in AC minus B square strictly less than 0, because the whole thing is valid, because then minus B square is strictly less than 0 is valid. What I want to say is that for a equal to 0, you cannot use the expression that I have used for gxy. For a equal to 0, this expression for gxy is invalid. This does not make sense. So, for a equal to 0, you have to go back to the old expression and write that gxy is 2bxy plus cy square. So, this can be written as y. So, gxy is equal to y into 2bx plus cy. So, if y and 2bx plus cy both have the same sign, it is positive, both have opposite sign, it is negative. So, here again I can find around 0 0, at 0 0 it is 0, again at around 0 0 I can find points where this is positive, gxy is positive, and other cases gxy is negative, telling that xy is a saddle point. So, again we conclude that 0 0, sorry, no, x 0 0 in this case is 0 0, sorry, I will just write down 0 0 is a saddle point. So, here also we conclude that if a is also equal to 0 and AC minus B square strictly less than 0, 0 0 is a saddle point. So, all the cases, whatever be the value of a, 0, positive, negative, 0 0 is always a saddle point in this case. So, let us summarize. So, let us make a summary. So, I have gxy given to me with ax square plus 2b xy plus cy square. Assume, so first assumption, assume AC minus B square is not equal to 0. If I assume that, then what I have is the following. If AC minus B square is strictly bigger than 0, then if A is strictly bigger than 0, it implies that 0 0 is the minimizer. So, if when 0 0 is the minimizer of gxy, it is the local minimizer of fxy, because fxy is equal to fx naught y naught or f 0 0 plus that quadratic term when they are this fxy value is almost equal to this part, the quadratic approximation when xy is very near 0 0. So, that is this is only valid when you are talking about a local minimizer. So, whatever is if 0 0 is the global minimizer for this quadratic function, it is actually a local minimizer for your original function. Basically, this condition AC minus B square is strictly greater than A is strictly bigger than 0, then these two conditions tell you that AX square plus 2BXY plus CY square is actually a convex function, right. And here convex function which is non-negative, and of course 0 0 is a minimizer. When a convex function, and since 0 0 is the critical point and this is the only critical point, so that has to be the minimizer. So, every critical point of a convex function is a minimizer, that is exactly what we discussed in the last class, and so this is what we have. So, this is actually deciding convexity. Then if A is strictly less than 0, basically if this happens and this happens, then 0 0 is the maximizer, it is the global maximizer of the quadratic function. Please understand, this is not local, these are global. So, whatever is the global maximizer or minimizer of the quadratic form, quadratic function is the local maximizer of the original function. Now, we will come to the case, our expression we had x naught y naught, we did not put x naught y naught equal to 0 0. Now, we will come to what is called the general form of the quadratic expression. Now, we will take a general quadratic expression. So, what is a general quadratic expression? So, now we will have a general quadratic expression where our g would be given as, we will write g tilde xy as some k. K in our case is f x naught y naught, A x minus x naught square plus 2b x minus x naught into y minus y naught plus c y minus y naught square. Now, in this case we will again assume AC minus B square is not equal to 0. This is something which is important for us. This has to be maintained. This will imply that x naught y naught is the only critical point. So, you have to assume this, and this will imply this is the only critical point. So, this is a kind of very important thing. It is actually this is a determinant which we will cannot speak now in this structuring, but okay. Now, those who know linear algebra, they would understand we are talking about positive definiteness and positive negative definiteness of Hessian matrix of the functions. So, but we will not get into all that. That is just a little bit of name dropping, which is not a bad idea sometimes. Now, what would happen in this particular case? So, we have to determine x naught y naught. So, again if AC minus B square is strictly bigger than 0, then A greater than equal to 0 implies x naught y naught is a global minimizer. For G tilde. Okay, you might ask me, what about, you did not write anything about AC minus B square in this particular case, the first, the AC minus B square equal to 0, less than 0. AC minus B square when it is less than 0, you have already seen that 0 0 is a saddle point. So, basically it is nothing. But the saddle point that we talk about in calculus is not the saddle point in the sense of modern optimization, and that has to be understood. So, and again then if this, then if this, else if A is less than 0, it implies that x naught y naught is a global maximizer for G tilde. If AC minus B square is less than 0, as before it would imply that x naught y naught is a saddle point. So, earlier we have basically shifted x naught y naught to the origin, now we have said that if x naught y naught is an odd point, the same story will work. So, we did our calculations in the simplest setting of x naught y naught to be 0, and then we worked with we have just brought our intuition up into the general setting. So, can we translate? So, this is the general quadratic form for which how we determine how x naught y naught is a minimum. Can we translate it to the function where it is a general quadratic form, but with the error. So, we will, when we will take x and y very near to x naught y naught, we will forget about that error, and here we will form our AC minus B square, So, forget the error, forget error for a little time, forget R2. Really you shouldn't, but all practical purposes let us forget R2, and then you construct what is called D. AC minus B square, if you write, then it will become 1/4 of this into this minus this, but this 1/4 tag you do not have to take into account, just write that, because once you are talking about something is bigger than 0 or strictly less than 0, so you multiply by another positive quantity, it does not change the sign. So, what you have to do is write that this is called the discriminant, D is equal to discriminant and that is nothing but AC minus B square, that is del 2f del x2 evaluated at x naught y naught into del 2f del x2 into del 2f del y2, and this is C evaluated at x naught y naught, not C, right, 2 of C basically, minus del 2f del x del y evaluated at x naught y naught, this thing whole square, AC minus B square. So, this is your discriminant, this is called a discriminant which you construct from this ABC. Now, write the same story which is here, and now change your G tilde with F, because you have forgotten the R2. So, your G tilde is playing the role of F, your K is playing the role of F x naught y naught. So, you might say that okay, I am not very comfortable with forgetting R2. I understand everybody who is much more clear, or who is more erudite will not want to forget it, but for us the same story can be written. We will write the same story we have written for this, now which I will write down. If D is greater than 0 and del 2f del x2 at x naught y naught is strictly greater than 0, it implies x, the same AC minus B square, whatever we have written for the other one, x naught y naught is a local minimizer. If D is greater than 0 and del 2f del x2 x naught y naught is strictly less than 0, it implies local mean. If D is less than 0, it implies x naught y naught is a saddle point. and d equal to 0, no conclusion. And with this we conclude today's lecture. Hope that you would go through all the calculations I have done. This is a slightly tougher thing. Thank you.